Today I want to talk about Zig interfaces, because making an interface in Zig isn't really straightforward. Unlike interfaces in Java or traits in Rust, interfaces in Zig are not abstract types. They are much more like containers. In most languages, an interface represents a contract, a set of behaviors that an object must implement. In Zig, the way you need to think about interfaces is reversed. An interface points to an object with a specific behavior. Alright, so let me guide you through the reasoning to create an interface step by step. Let's say we are building a simple drawing app in which you can draw squares and triangles. Our application currently does something pretty simple. It has two arrays, one for squares and another one for triangles. To draw them on the screen, we iterate through each array. This works well, but when we start adding more shapes, we quickly run out of screen. So instead, I want to have a single array able to store any shapes, and a single for loop. In order to do this, we need to define a shape interface. So we need to create a struct named shape. Because our goal is to be able to do something like shape.draw, we need to define a draw method. Okay, but what do we put inside it? This draw function should call the actual underlying shape, which is either a square or a triangle or something else in the future. So before being able to do anything, we need to actually store this shape. But what type should it be? We can't use triangle or square, otherwise it would only be able to store a single type of shape. Because Zig is strongly typed, the only way to store different data types at the same place is to use a pointer that doesn't know anything about the data it is pointing to. We cannot use regular pointers because even though pointers store memory addresses, they are typed to help the compiler know how to interact with the data pointing to. Here, we want a pointer able to point to any type. In C, we would use a void pointer, but in Zig, we cannot use void because void has a known size of 0 bytes. Instead, we need to use an anyopaque pointer because anyopaque represents a type with an unknown but non-zero size. When we make an anyopaque pointer point to an object, we lose the type information. That pointer doesn't know anything about the underlying type. That's why we often talk about type erasure, because we lose the type information. Inside the draw method, we can't do something like self.shape.draw. If we try, we get an error like no field or member function named draw in anyopaque. So we need a way to turn this anyopaque pointer back to its original type. We can do this by using the built-in pointer cast function, which can cast a pointer of one type to a pointer of another type. In practice, it looks like this. Oh, you wished. Because this doesn't work. It doesn't work because of alignment. And if you don't know what data alignment is, I'm planning on making a video about it soon, so maybe it's already out and you can watch it. Otherwise, subscribe. But in short, data isn't stored at any random address in memory. It can be, but it's usually a bad idea, and for some CPU, it's straight up illegal. So the data needs to be aligned. Aligned means that any primitive object of n bytes must have an address that is a multiple of n. For example, U32, which is made of 4 bytes, needs to be stored at an address that is a multiple of 4. For a struct, its address must be a multiple of the alignment of its member with the largest alignment. For example, if we have a struct with a U16 and a U32, then the U16 member has an alignment of 2, while the U32 has an alignment of 4. So the struct has an alignment of 4. The reason we care about this is because in Zig, each type has an alignment. Now the question is, what is the alignment of anyopaque? An anyopaque can virtually represent any type, each with a different alignment. So the alignment of anyopaque can only be the smallest one, which is 1, because any memory address is a multiple of 1. Now, we need to talk a bit about pointers. When you create a pointer, the Zig compiler will build a standard built-in type pointer object to store information about the pointer type. One field of this object is called alignment and corresponds to the alignment of the data that is pointed by the pointer. It is not the alignment of the pointer. Okay, so for a pointer to a U32, it's 4. But if we use an anyopaque pointer, then the alignment is 1. That's why when we try to cast our anyopaque pointer to a triangle pointer, we got an error telling us that pointer cast tried to increase the alignment from 1 to 4, which is not allowed. This error message also tells us that we can use align cast to assert pointer alignment. And in the documentation, we can read that if you have a pointer or a slice that has a small alignment, but you know that it actually has a bigger alignment, then we can use align cast to change the pointer into a more aligned pointer. This is exactly the situation we are in. We have this anyopaque pointer with an alignment of 1 that we want to cast to a triangle pointer, for example, with an alignment of 4. Okay, so that was a lot of yapping just to tell that to convert our shape back to its original type, we first need to use align cast to change the alignment value of the pointer type, and then use pointer cast to change the type. If I go back to our code, then we just need to add align cast like this. Yep, that's it. That's all we had to do. You know, I could have just said that right away, you know? Aren't you glad that you're watching this video? Alright, what are we doing already? We're building an interface to be able to call the draw function of each of our shapes. But we can't actually do this because inside the draw function of our interface, we don't know what type we're actually dealing with. The trick here is to define in each and every struct a function that takes an anyopaque pointer as an argument, and inside these structs, we can cast to the corresponding type, and now that we have a type variable, we can call the draw function. Now we just need to be able to call this function from the draw method of the shape struct. We can do that by using a function pointer, and we can use this function pointer to call the function with the opaque pointer as an argument. So when we create a shape, we give it a pointer to the underlying shape and to its draw opaque function. Okay, so this works, but creating this draw opaque function in every struct is a bit annoying. So instead we can use some comp time magic to generate it automatically for us. Inside shape, we can create an init function that will create a new shape object, given a pointer to a square or a triangle or any other shape. Once again, here, we want to make a function capable of taking one parameter with different possible types. But this time, the situation is different. When we are going to use shape.init, the concrete type of the argument is known at compile time. So we can use type inference by declaring the function parameter as any type. Now this init function is able to take any type of argument, so we are going to be able to feed it a pointer to a square or to a triangle or to any other shape we want. And we can store it inside the pointer field of our new shape object. The idea here is that at comp time, we can know the actual type of the shape we are giving to the init function. Using type of, we can store this type in a constant. And if we know the type, we can create a similar function to the one we just created inside our triangle and square struct. If we take the function defined in the triangle struct, I just need to modify it a little bit to use the type t we found using type of. And now we can store that function inside the function pointer. Unfortunately, this doesn't work because Zig doesn't let us define functions inside other functions. So instead, we can create a struct and put this function inside it. Don't forget to update the function pointer to point to the function inside this struct. And that's it. It works because at compile time, the compiler will create a new init function for each shape. We can now create a shape object from any actual shape without needing to add anything to the older structs. So let's summarize. To create an interface, we need to create a struct with an anyopaque pointer to store a reference to the underlying object. We also need a function pointer to point to a function that takes as a parameter an anyopaque pointer. To make our life easier, we can create an init function that takes an anytype pointer, then get the actual type, and generate a function with the same signature as the function pointer. And finally, returns a new object with the pointer and function pointer. The goal of this generating opaque function is to call the underlying function that all of the underlying objects must implement. And then we can add a method to the interface to call this opaque function with the anyopaque pointer. Okay, so this is a common pattern we can use to define interfaces, but there are a few variations, and I want to show you some of them by looking at the standard library. If we take a look at standard.random, we can see the anyopaque pointer and the function pointer. Here, this function pointer has two parameters, one for the anyopaque pointer and another one that is used by the actual function. So if your function needs some parameters to work, you can just add them after the anyopaque pointer. We can also see an init function which takes an anytype pointer as a parameter. Inside, it gets the type of this pointer using type of, then it creates a struct with a function which signature matches the function pointer. And finally returns a random object containing a pointer and a function pointer. So this interface has the elements we talked about. Now let's focus on the differences. First, this init function takes a second parameter called fillFn. This is not a function pointer, but a function body. They are both types, but a function body must be compile time known, while a function pointer can also be known only at runtime. So this parameter corresponds to the concrete function, like the draw function we have in all of our shapes. Here, it's comtime, so we can force the first parameter to be of the same type as the pointer. And inside the fill function, inside the gen struct, we use this function body to call the actual function. The reason this is interesting and maybe a bit better than what we did previously is because this init function clearly specifies the function our concrete types must implement, while previously it wasn't as clear that our shape must implement a draw function. Another difference is the use of many asserts. Here, because init uses an anytype parameter, well, we can potentially give it anything. So using type info and a few asserts, we can make sure that we have a single item pointer to a struct. This makes the interface more robust. Okay, now let's look at a different example. Let's look at the standard mem allocator interface. Once again, we have an anyopaque pointer, but this time we don't have a function pointer, but we have a vtable, or a virtual function table, which is a struct containing multiple function pointers. This is a pretty common pattern when we want to create an interface with multiple functions. So it's the same idea, but this time there's no init function, so you need to do a little bit more work. If we take a look at the debug allocator, this function returns a type, which is a struct, and inside it we find the allocator function, which returns an std mem allocator containing a pointer to self and a complete vtable. And I think that's enough for today. Okay, I hope that was helpful. Subscribe and tell me what you would like to see next. And well, actually, do you think I should do like a shorter version of this video with maybe a little bit less details and like going straight to the point? I feel like this could be a good idea. I don't know. Anyway, goodbye. Thank you for watching. See you next time. Tralalelo tralala. Bombardilo crocodilo.